SwayamPrabha. Digital India. Educated India.
Welcome to Basics of Noise and its Measurement. Today is the 5th day of this particular week, and we have been discussing over this entire week the concept of discrete Fourier transform, and we will continue this discussion today. What we will cover today are two specific topics. The first one is FFT, fast Fourier transform. And then the second concept we are going to discuss today is inverse of DFT, inverse DFT. So, we will start with FFT. FFT. So, DFT was discrete Fourier transform. FFT stands for fast Fourier transform. Most of the times when you hear in industry or in signal analysis, you do not hear DFT, rather you hear FFT. So, we had seen that the DFT of any signal xt is given by this relation xk equals right, or we had explained it also, right, or we had also explained it as, expanded it as yeah 2 pi, yeah, you are right, 2 pi n k over n times I. So, this was x n cosine of 2 pi n k over capital N plus sine of 2 pi n k over capital N, and there is a negative here and there is an I here, and this entire thing is in parenthesis. So, this is the discrete Fourier transform for a function x n. Okay. In this function, we have n outputs. What are those n outputs? x0, x1 times x n minus 1. And then each output what is it? In each output I have n sums, is a sum of n terms, right. It is a sum of n terms, and then to compute each term you have to find out its cosine and sine and so on and so forth, right. So, essentially when you do this whole computation for n different terms, you have to do something like n square computations, and it is not an exact n square thing. So, it is something whose order is something like n square computations, order is something like n square computations. So, it is a very intensive process, it's a very intensive process. So, that is what FFT is all about. FFT is basically same. So, if you can, so this you do using this regular approach, and you will end up by having a number of computations will be something with an order of n square. If you do it in a faster way and a smarter way, the formula is the same, that mathematics does not change. Then you call it a fast Fourier transform. This is the FFT because it's faster. Okay. So FFT or fast Fourier transform, it reduces number of operations. And typically it requires not n square, the order of the computations is not n square, but order is something like n log of n. If it is somewhere closer to this, then you say, oh, it's fast. It's fast Fourier transform. And there are several algorithms to do that. And one very popular algorithm is called Cooley-Turkey algorithm. Then there is another term, this is very popular, Cooley-Turkey algorithm. There is another algorithm, not that much popular, Cornelius-Langzos. And then there are other algorithms, Brun, Rader, prime factor, and so on and so forth. But the point is that fast Fourier transform is essentially same as DFT. It's a faster way to do these computations, and if you do it faster, you call it fast Fourier transform. Most of the algorithms which are being used by standard codes like MATLAB, Mathematica and things like that, I think they use FFT approach. So that covers the topic of FFT. The next topic I am going to cover is inverse FFT. Actually inverse DFT, but inverse FFT is also something very similar. So when we do DFT, our aim is to get xk from xn, right? In DFT, input is xn, which is time dependent, and output is xk, which is frequency dependent. In inverse DFT, our input is xk and output is xn. Okay. And how do we do that? So if I know, if xk is known, then xn equals 1 over capital N and so excuse me, this time I will be adding up on the index k, okay, because I have xk's, xk e to the power of I 2 pi n k over n. So formula is pretty much the same, except instead of minus I you put plus I, and instead of adding on the index of n, you here are adding over k. But k and n, I mean you can interchange them, it does not matter. So I will just make it available in trigonometric format. So it is 1 over n k is equal to 0 to n minus 1 xk cosine of 2 pi n k over n plus I sine of 2 pi n k over n So that is my inverse transform. So what does it tell me? That if xk is known, if I know all the frequency components, and then using those frequency components, I can get back my time series data. And if I have time series data using DFT, I can get frequency data. From frequency data, I can back calculate time series data using this thing. Okay. So that is all what I wanted to cover in this lecture. In the next lecture, we will change tracks and we will go back to instrumentation and about what kind of considerations do we have to think about as we select different types of instruments for noise related measurements. So thank you very much, and we will meet once again tomorrow. Thanks.